Good morning. Good morning, everybody. Good morning. Good morning. Slightly better, I think. Without breakfast. Okay, first of all, before I start the talk, sir has gone, but let me place on record my sincere thanks to this Ganpat Parsekar College for inviting me and considering me fit to give a talk of this kind. I am always eager, but one should get a chance. So I got a beautiful chance, and the most important thing for you students, you may not be knowing that I am now giving this lecture in the presence, in the beautiful presence of my students. On one side I have Vishwesh, and on the other side I have Sienna. These are all my B.Ed students, and today when I see them as assistant professors, I am really proud. And I have my PhD student also, Mr. Uddesh Natekar. I would say later, Dr. Uddesh in a few months becomes Dr. Uddesh, and others also known to me. Ushali is there. One more student is, I forgot his name, is there. So it's a great thing to be here, and it's good, as Parsekar sir rightly said, as we entered, the scene was very good. It was giving honor to all the mathematicians, whether they are from India or not. Maths doesn't know that it is an Indian mathematician or a Western mathematician. Maths has got no boundaries. In fact, no knowledge has got boundaries. So that's the whole beauty was there when we came in. But we are restricted to the persons. But mathematics is not just persons. सिर्फ लोग नहीं हैं. Mathematics is something that is there in your mind and we can see around it. उसके लिए mathematician होना जरूरी नहीं है. We are all interacting with mathematics. So that's why I wanted to break it. I didn't want that mathematics मतलब वो maths का teacher या formula. It's not like that. It is beyond that. So today I wanted to dispel that from you. So today we are celebrating Ramanujan's birthday, but they are all mathematicians. Fine. But you need not be mathematician to understand mathematics. In fact, we are all understanding mathematics, and today we will be doing some things and we will be seeing the presentation. I have made it in such a way that everybody should enjoy, because mathematics is something that we all are in us. Okay, we will see that today. The wonders of maths that we can see in nature. It is not only the formulas that we have in the book, it is beyond that. And all the formulas and all that people have written and found about maths, they have been inspired from nature itself. That's how the entire maths comes. So you will be amazed to see how much of maths is there. And let me say, there cannot be any universe, any nature without mathematics. You will see that the entire world is functioning because of mathematics. Whether it is a man-made world or whether it is a natural world, entire thing is governed by mathematics. So which formula, which theory, that you may not know, but let me say, nothing in the universe works without the permission of mathematics. One or the other formula is going on, whether it is physics or chemistry and even biology and zoology. We will be seeing that, because many of them, they feel biology, zoology has nothing to do with mathematics. We will see that today. Okay, can you see this picture? Okay, this is for something for you to see. And it looks beautiful, it's amazing, isn't it? Everything in nature looks beautiful. Flowers look beautiful, trees look beautiful. Today we will see why they look beautiful. Okay, see the beauty. Don't you think it's beautiful? But there is something extra over there which is puzzling. Okay, by the end of the talk it will not be puzzling. Right now that curve is looking nice. One creeper is there, pleasant is there. But I have put, you will see something else is also there, which is a little strange. That we will see today. Okay? Next. Mathematics is called the queen of science. I have put a few texts, so don't be perturbed. This is the starting point. I have to clarify certain things. After that, you will be learning only from pictures. Okay? And maybe a small exercises I will give you, you will enjoy. Mathematics is called the queen of science. Have you ever wondered why? It has a considerable contribution to a better understanding of nature's beauty and the world around us. When we say beauty, you never think of maths, isn't it? But let me tell you, anything that looks very beautiful definitely follows mathematics. What does it follow? That we will see. Okay? The work of mathematics being to being to the mind numbers, equations, and the hidden relationships between them. Isn't it? So when we are seeing something, we find it is beautiful, we find it is functioning. The question is, how does it look beautiful and how does it function so well? There is definitely some mathematics behind it. Maths shows up everywhere. In our daily lives, in our classes, we least expect. Often in high school and even universities, mathematics is very theoretical. That's the problem. And it's hard to see its use in real world. We feel that, okay, equations, close it in the book, that's maths. When we go in the garden, maths, today we will see that. Let's increase our interest. Maths not only in garden, maths in you, maths in me, yeah. Let's increase our interest in maths by understanding and showcasing its real world application. Let me tell you, it's not just like that, it's called the queen of science. If you remove mathematics, everything else falls down like a card. Nothing else, no technology, nothing, no digital. Do you know why it is called digital? Just go home and find out why it is called digital technology. Digit means 1, 2, 3 are digits. Why it is, please write down, please keep a notebook and a pen with you. When you are in my class, that is required. Even on online lecture, I have done like that. There are some of your teachers who attended my online lectures. Online also you have to keep a book and pen. Okay. Teachers can also keep, because today now we are all students. Okay. So one homework right now I am giving you. Go and find out why it is called digital technology. There will be many more things. सिर्फ हिलाने से नहीं होगा, वो लिखना है. Because many things will be there. It is better you note down. You have please give him a book and a pen. I have pen, book you have to manage. Okay, maths can be frustrating. You will all agree. Yeah, man, maths is frustrating, boring, arduous, just plain hard at times. 10 tuitions you require. Am I right? 10 tuition classes, 20 textbooks, 300 friends can't help you learn maths. What is so hard about it? Nevertheless, from preschool onwards, we learn concepts from counting to calculus. Beauty of mathematics is hidden in. Now this is where it comes. We don't look at this. Now we find all these things you have put here, they look beautiful, isn't it? You have put the cutouts, they look beautiful. Any reason you know why it looks beautiful? So that's what I'm saying. How do they, and why it will not look beautiful, at what could be done to make it not look beautiful? What may be the reason? It looks beautiful, fine. What may be the reason it doesn't look beautiful? Okay, so beauty of mathematics is hidden in harmony. You know, we say we live in harmony. That's a different thing. We are talking about material harmony. We go to somebody's house. Oh, the house looks very beautiful. At one look you say, you don't know about the architecture, you don't know about the measurement of the hall, you don't know anything. But as soon as you enter, what do you say? Oh, it looks beautiful. Why? It's harmonious. Okay, the height, the breadth, the color, the thickness, everything is harmonious. So mathematically it is followed. The architects and the painters, they have taken into consideration. That's what I'm saying. So it is hidden. Mathematics remains hidden. It doesn't come with selfie. See, look at me, I am mathematics. Mathematics doesn't do that. It is hidden. Okay, patterns. It shows its beauty through patterns. It doesn't claim, see, you are having beauty because of me. Because mathematics knows very well, you cannot have beauty without me. You know, that's the fact. Mathematics doesn't have to take selfie. When your selfie looks good, it is the mathematics in it that looks good. Okay, we'll see that. I have brought some examples. I'm sure you'll enjoy. Patterns, numbers, forms, symmetry. Symmetry is something that we will see. Whole world, you know, our body, we are all symmetry. Any idea? Our body, human body is symmetry. What kind of symmetry? Bilateral. Fantastic. So we will be seeing that. It is an international language. Mathematics is an international language. Anybody understands 1 + 1, 2. Isn't it? It's an international language that helps us to describe the world around us. If I say there were many people, that's got no sense. Isn't it? Few people came. 4 people came. 5 people left. That's more exact. How many people are coming to your house for dinner? Many. How will you prepare? It doesn't, many, few doesn't have any value. So, therefore, where is the sun? Far away. There is no far away. You know, it has to be exact. Am I right or not? A little bit more, life on earth is gone. Our position is so fantastic. If you are on Mars, first of all, how will you live in Mars? That's a different story. We can not only count with numbers, we can describe patterns with them. Number patterns. Have you seen number patterns? Isn't it? Odd number, it's a pattern. isn't it? Even number is a pattern. It's the first pattern that you learn about maths. Symmetries are everywhere in the world. In everywhere you see, there is symmetry. If there is no symmetry, then it will not look beautiful, isn't it? So symmetry. Nature hides numbers, equations, proportions. Just take a look around and enjoy its beauty. That's why I said, yourself also if you see, there is play of maths, and around you see, it's nothing but a play of maths. In fact, maths are present in it. But in many cases, non-significant areas of our lives, we usually do not consider it as something beautiful. Maths, beautiful, we feel something. Maths cannot be beautiful. Maths is hidden, isn't it? From counting numbers, taxes, geographic coordinates to music. Maths. Music is full of maths. That's why I said, once maths is removed, everything will fall down. He's, I think, MFA. Yeah. If I remove maths, his entire MFA will collapse. Ask him. Entire fine arts will collapse if there is no maths. Are you getting? So, because they use the principles of maths. Today's many of the things he will be aware of. Okay. So, the beauty that we talk about, the ideas that we have, many of them are, ruled by the wonders of maths. Let's try and see that. Where can we find it? In almost everywhere in nature, landscape, species of plants, animals, including humans. Mathematics is the key to our attraction, isn't it? We are attracted to people, we are attracted to things, we are attracted to something that we can see, some places. Wow, this place looks beautiful. If you analyze it, you will find out that something is there about mathematics, that's why it looks very beautiful. What is that mathematics behind that beauty? That is the whole thing. So, when anything looks extremely good, there is something to it. Okay. So, we can find it even where we do not expect to meet. For example, our mobility depends on it, our walking, our travel, everything. It is also an essential tool in engineering, biology, philosophy and arts. It is commonly known that mathematicians see the beauty of mathematics. They see the beauty in mathematics itself. That is why they are mathematicians. These people whom we are talking about, we are looking at mathematics as a subject. They look at mathematics as a beauty, the mathematics itself as a beauty. I am trying to show you that in nature there is mathematics, so that I can attract you towards mathematics. But they were attracted to mathematics itself. That's a higher level of attraction. It is commonly known, the beauty of mathematical formulations lies in their ability to describe the phenomena. So they gave us all the description. It's a higher level mathematics that we are talking about. I am trying to show you what we can see and learn. They could talk about something that we cannot see, it is hidden within. Okay. They were working at a very higher level of mathematics. I am trying to show you what we can actually see around. The natural world often displays models, patterns, phenomena we see in mathematics. The vast majority of animals on earth exhibit at least some form of symmetry. So let's begin with symmetry, because that is something that we all know. Snowflakes, we all know about snowflakes. Not that we have seen it, but you must have seen in movies or in videos or even in pictures, you must have seen snowflakes. This is one of the most popular examples in which shows symmetry in nature. Symmetry, almost everything there has to be symmetry, otherwise it will not look beautiful, it will not function. In particular, they indicate six-fold radical symmetry whose arms have identical elaborate patterns. Let's have a look at snowflakes. You have seen snowflakes? Okay. Many of the decorations, they use snowflakes, because we don't have the snow that we see, in the mountains and all, we see snow. It is made up of flakes. They are not powder, they are flakes. So this is how snowflake looks like. We have not gone to Kashmir or anything, but people there, he must be aware of all this, because you all see patterns. No? So each snowflake, can you see the design of the snowflake? Are you all able to see? Yeah. So that's why, so see the symmetry. So it is not just, at random something shining. No. The full geometry is there when we talk. So let us see snowflake. It looks so beautiful, but there is hardcore science, maths behind it. Each snowflake has identical arms, but there are no two snowflakes that look alike. So great, no? So many snowflakes. It is like human beings. We are all similar, but we are also different, isn't it? So in the same way, these branches, six arms of the snowflake, and each snowflake looks different. You may wonder, what is so different in each snowflake, isn't it? There is hardly anything to be different, but it is. See, so don't you feel it is beautiful? You never thought that when we talk about snowflake, it will be beautiful. Now you see sunflowers. Have you seen sunflowers? Okay, some of you may have seen, some of you may not have seen. Sunflowers, I think if you go to Karnataka, Hampi, those areas, you know, some areas of Karnataka, I don't know, maybe Maharashtra also, they grow sunflowers. You should have a visit. When you actually see the field, you know, it is mesmerizing. You won't know from which side to take photo because they look so beautiful, very beautiful they look. So next time you go around, take a photograph of in any chance of getting to see sunflowers. You don't have to go far. I think across the border somewhere you should be able to see. Maharashtra side also, I think there are. Karnataka side I have seen. Okay, the fields, they look very beautiful. Even if the single flower you may not find it very beautiful, but that is also, but the fields look very nice. These beautiful flowers show radial symmetry. We have bilateral symmetry. They have radial symmetry. That means the symmetry is across the radius. So that means it is circular. Flower is circular, isn't it? So as well as numerical symmetry, that we will see a little later. Fibonacci sequence is a little more interesting, that we will do a little later. Okay, so when they are looking beautiful, it is because they follow radial symmetry. Now you see bilateral, because I thought there may be students who don't know, so I thought I will bring something for them to understand what is bilateral symmetry. This is divided along the length, you know, both sides of us are equal, isn't it? One leg here, one hand here, one hand here, one leg here. We are symmetry, isn't it? So in the same way, if you have now, but if you look at the, you know, the turtle at the bottom, you see two types of symmetry you will find, isn't it? It is from the top to bottom and from the front to back, both sides of symmetry. So see the wonders of nature. That's why it looks so beautiful. People want to keep turtles as pets, which is wrong. You should not, but I am just saying. So when we look at it, we don't know that how, because the body is so well, symmetry is followed in the construction of this. So nature has followed a lot of mathematical fundamentals. That's why nature looks so beautiful. And another thing we should remember about nature is it is very, very economical. Nature is very economical. That means it will not waste anything. We have got only two hands. Sometimes we feel we should have three. No, when more work is there, don't you feel like that? Oh, if I had two more hands, two for mobile and two for something else. No, you didn't feel like that? Two for like this, and two for like this or something. I don't know. Two for eating food. You imagine how nice it would have been. No? Two for mobile and two for eating food. Imagine your condition. You would never leave that mobile. No, just at least for eating food, you will leave that mobile. Am I right? Some of them are wishing like that. Yeah, madam. Yeah, with two I can do my mobile and with two I can write my journal. Wow, nature didn't do that, sorry. So the point is, nature is very economical. The minimum with which maximum work, that's called optimization. Minimum with which maximum work can be done, that is the lookout of nature. Nature will not give you extra. Nature will not give you extra because we have got two eyes. We feel like और एक आँख यहाँ पे होता तो अच्छा होता, उधर का भी दिखता. It doesn't happen. We don't need it, so it is not given. Simple. You may feel like you should have wings. You are not given because you don't need it. So if you see, sometimes we feel what the other person had, you also need. You don't need it. That is the whole idea. Okay. So let's see. So this is how bilateral symmetry. So you will see that nature is not just made like that. There is a purpose for that, and everything that is made has a mathematical formula or a mathematical idea behind it. Otherwise it cannot be. Now you see these animals, you see some of the marine animals. When you look at it, you don't feel that there is anything in it, isn't it? Now you see animals with radial symmetry have parts arranged around a central axis. We all study, so when we study maths, see the beautiful things that are there in maths. We study about symmetry, we study about axis. But do we study it with respect to octopus or any sea animals? We don't. That is the problem. That is where the problem comes. So when you are teaching about symmetry, begin with animals. Maybe then the interest will, then you are not studying about symmetry, you are studying about the animal. So you are trying to find what are the symmetry in different animals and why do they have that symmetry? Not simply for design. Nature doesn't do anything just for beauty. Let me tell you that. It may look beautiful, rose looks beautiful, flowers look beautiful, but nature's intention was not to make it beautiful. There is a different intention altogether for nature. So they didn't make them, though it looks beautiful, isn't it? The symmetry is there, so the animals, they look so beautiful, isn't it? It looks beautiful, but that is not the purpose for which it was made like that. So these are the radial symmetry examples. You see the different examples that we can have for radial symmetry. Next. Have you seen starfish? I don't know, some of you may have seen. Now you see the starfish have eye spots, all the 5, there are eyes in all the, and the very interesting character this starfish is, end of each arms rather than on the head, the middle is the head region. Those who are with zoology, they will know. One advantage is that even if one part goes, it goes and it comes, it regenerates. It is like that. So it is like एक हाथ गया होगा दूसरे दिन में दूसरा आया. It is like that. So you may also feel चलो ये हाथ बोर हो गया दूसरा आएगा. You may feel, but you cannot have. Only starfish can have. But starfish doesn't have the brain that we have, isn't it? So I wish, madam, we were like starfish. It doesn't happen like that. Okay. It is easier for organism to regenerate lost parts. So what I am saying is that it has not given the radial symmetry just for beauty. There is more purpose to it. So you can go and find out more about it, but I am just giving you a hint that the things that we are seeing in animals and plants and mathematics, it is not just for beauty or for fun. There is more to it. So when you study zoology or when you study about mathematics, please put both together. When you study zoology, see the mathematics part of it. When you study mathematics, see whether it is there in zoology, whether it is in biology. That is how one should look at it. Now you see, radial symmetry and bilateral symmetry. So this starfish has been given radial symmetry because that's what it requires, whereas a housefly and many other insects have been given bilateral symmetry, isn't it? So both purpose is different. So maths has given different ideas to be for the construction of these different creatures. Okay. Now you see, which is this animal? Anybody can tell? On your right. Pardon? Find out. Pardon? Lobster. Yes. In case you don't know, you should find out, because you go to the hotel and all, you eat very nicely. It is same fellow. Same fellow it is. Yeah. No, I'm just where to ask. No. So there also, when we are eating fish, so today when you go back home and you eat fish, or what do you feel about chicken? What kind of symmetry? Chicken dynamite. So I am saying, so don't you think that we are talking about maths? Maths is not there in the textbook. Maths is there around. Do you think maths is there in your hand also? We'll see. Now you see the flowers. Isn't it? They look so beautiful. The reason? Symmetry. Isn't it? Symmetry gives them the beauty that they have. Isn't it? Now later we will see something more about the flowers and their petals, but here it is about the beautiful part, that is, it is symmetrical. We give these carnations as for our friends, for our birthdays and all, we give carnations. It has got bilateral symmetry, and here in the sunflower you have got radial symmetry. Are you all enjoying? Are you all getting some idea? Okay. The natural world will always arrange itself in such a way to expend the least amount of energy to get the greatest benefit. That's what I was telling you. Nature will never waste anything. If 2 hands are given, that's it. You don't need the third one. So nature has got. This is why tree branches. We look at the tree and we feel, oh, what can be maths in a tree? Tree is full of mathematics. Inside the tree and the tree itself, full of mathematics. How? That we will see. This is why tree branches grow by spreading out while filling space efficiently, why atoms arrange themselves in specific energetically favorable formations, and by spirals and circles. If you see in nature, most of the places you will find circles, isn't it? All our things, entire planetary system, if you find circular, isn't it? Everything is revolving, rotating, everything is circular. Okay, and then another we find is spiral, isn't it? Spiral we will find. The first slide itself, if you remember, I had shown a spiral, isn't it? The green one was a spiral. So we will see. So nature has got a tendency to take circles and spirals. What could be the reason? We can see. Okay, so because these are energetically favorable shapes. Why circles? And because earth also circular, isn't it? Spherical, but it is coming in a circular form. So everything like that. So nature has chosen that shape. Nature has chosen the shape of circular and spiral. The reason? Energetically favorable, isn't it? Less expense of energy compared to other shapes. Okay, so that's why it is taken. Now you see, what can you see? It's very difficult to see the snake, isn't it? It is so well camouflaged with the surroundings, isn't it? It is called a diamond back. Why do you think it must be called diamond back? It has got. So snake is also using mathematics. In fact, nature has used it on snakes, isn't it? Snake doesn't know that it has got diamond back. Do you think the snake knows? Snake doesn't know. We know. Do you think the snake knows he is called diamond back? Does the snake know his name? I can't hear. We know he or she doesn't know that his name is such beautiful and he is shown on the PowerPoint. He doesn't have to take selfie. He just have to roam. See, I am searching for him on the internet and I am showing you. He doesn't have to bother because he is so beautiful. People will hunt for him. We are like mereko bhi dekho, like that we are. Many people depend. No, because the snake doesn't bother, because he knows I am beautiful, they will hunt for me. Because I have diamond back. He doesn't know what's there on his back. Like that. So one point here is that how mathematics is used even for camouflaging. You must have seen animals, some of the owl, some of the, this chameleon, they camouflage. That's called camouflage. It means they mix with the nature so well, you can't see. Even if a tiger stands in the middle of the grass, you cannot see. It's a huge animal because they camouflage, because of the stripes. So the camouflage is another, weapon given by the nature to animals to protect themselves. So one of them is, this snake can catch some fellow sitting over here, isn't it? Nearby, if some fellow is there, he can easily catch because they cannot see. Okay. So many animals depend on mathematical ratios as both a form of camouflage and predation to catch. Okay. Meticulously organized patterns and color schemes can also be used as both way to attract and dissuade. So you want to attract the male, wants to attract the female. At that time, you understood, no? Nature also has got those, plants, animals, birds, insects, all have got this problem of attracting the female. That problem is not only in human beings, that problem. No, I am just telling you, Just you have to know, because you may think that only you are putting they are also putting their selfie, like this, you saw, no? Like that they put, and then the female will say, oh, she's good, he's good. He has got better diamonds than the other one. Okay, let's catch him. Have you not seen birds trying to attract the females? Yeah, they do. Let it be. Okay, you must have seen honeycombs. You are so much interested in honey. Honey khayenge, cholo, honey skin ko lagayenge, chamkenge. No. Look at the honeycomb. Yeah, honey, they are putting, Nowadays what happens, people put everything on the face, whatever they were eating. You have seen that kakdi lagao, haldi lagao, ye lagao. Usme honey bhi lagao. Eat honey. Morning, if you eat honey, that would be better than chipkane se acha. Andar, it should go inside. It will go to your heart and all that. If you put it on your skin, it will not go to your heart and lungs and all. It will remain on your skin only. So honeycombs. Why am I telling about honey? Honeycombs. I may get distracted. No. So mankind has been amazed by honeycombs. Hexagonal figures. Hexagonal, six-sided. Can you see the six-sided figure? Yes. See how the honeycomb is made. Nobody made it. They have made it. Exactly same. Bees are instinctively make this, but humans would have to use a compass and a ruler if they want to reproduce this. If we want to do this with the free hand, you cannot do. We can do this free hand, this structure? Definitely not, isn't it? Those who have done that Rangoli and all, they must have used some, some prototype or something. You must have used some stencil or something. You must have used for that. But honeybees don't have that. Don't you think that we should salute them? Definitely. And another thing, many of you may be knowing, if honeybees are not there, almost in a year, our world will collapse. Even if we are not there, nothing will happen. Imagine if human beings are not there on earth, anything will happen? Nothing. Yeah, that is very good. You are intelligent students. No, we think, our selfie everybody will see. For what? You are not producing oxygen. Honeycombs indicate wallpaper symmetry in which a pattern is repeated repeated unless it covers the entire plane. It is believed that mathematicians, that bees choose this structure as the most efficient to store most honey possible with the smallest amount of wax. You're getting? That's why, if you remember, I told nature will take everything and will not waste anything. In this shape, more honey can be stored and less wax is used. They use wax to make that. See? So that is why that structure. It is not just for the beauty part of it. You see? So don't you think that nature is teaching us many things? It is actually using, they are using mathematics. Don't you think that honeybee is using the mathematics? But the only thing is, honeybee doesn't know that it is called honeybee and it doesn't know that it is making hexagon. Don't you feel so? That is for us to discover. So let us discover like this. It will be nice. Any idea what is this? Next. Any idea? It's a very interesting study. That's why I brought for you to see. What is it? Yes? Okay, no problem. You see it carefully. I will come back to it again. It is the same thing, but yet another thing. Okay? We'll study about. Don't worry. You don't have to faint if you don't know. So it is, this research holds, this was a part of a research done all over the world, but I am taking it from one particular. This research holds exciting possibilities for the use of a slime mold. It is a slime mold. It's a mold. How we have bread mold, like that. It's a one kind of a microorganism. You see, this is after the experiment. What was the experiment and what we found, that I will show you. This is another same type of experiment. It is in the Petri dish. You know what's a Petri dish, isn't it? In the lab we have Petri dish. It is done in the Petri dish. So now why I have brought this to you and what am I trying to show you is that this research holds exciting possibilities for the use of slime mold models in the construction of future transport network. Just imagine this mold, this microorganism is going to tell us how to make network, road networks. It is going to, that is the experiment. So at the slime mold Physarum polycephalum is famous for solving a feat of engineering that took humans years to complete. Human beings could not do it, but the slime mold within hours it could do, within days. This slime mold is completely brainless. It doesn't have brain. It's a microorganism. Okay, and devoid of any type of organs or tissue. It is just multiplication of cells, that's all. At Hokkaido University in Japan, the slime mold was placed in a Petri dish, that glass, what you saw, that's called a Petri dish. And oats flakes, you know what are oats? We eat oats. So what they did, as a nutrition, they just spread it around. And they wanted to see how this mold will go and take that oats. You got it what I am saying? It is in one mold. Okay, you can go back. See, it's a mold and they have spread oats everywhere. And what it does, you can see the root it is making. You can see the road like tube-like structures you can see. It is making those tube-like structures for what? To reach to the oats. You are getting? Are you understanding what I am saying? So that's why. And then it will happen like this. You understood? Step by step it will come and it will make network. So that it goes to the other one next, earlier. Earlier. Within hours it will make network like this. So with the help of this network, engineers were able to make network, how to make a network of roads. They were able to take inspiration from a brainless microorganism. Isn't it wonderful? Yes or no? Isn't it? In Japan and many places they have done this, but I found it to be really great. Okay, so at Hokkaido University in Japan, the slime mold was placed in a Petri dish with oat flakes spread in a way that mimicked stops in the Tokyo subway station. With a matter of days, the slime mold created a network that was almost exactly same like the highly efficient Tokyo subway system. So Japan has got a railway system. This particular slime mold, it made a network which was exactly like Tokyo subway network. Don't you think that is marvelous? Isn't it? So I found this to be amazing. I said I will not stop. I could not stop myself from showing. I said at least 3 slides I will show them. Now you see this is the hour by hour they have done. First hour, 5 hours, 8 hours, 11 hours, 16 hours and 26 hours. How the slime has done the network that they are showing. Within a matter of days, the slime mold created a network that was almost exactly same as the highly efficient Tokyo subway system. Don't you think that nature is giving us something? With the help of that, they were able to find that this mold, this slime mold can give us ideas about how to make the network, isn't it? It may be communication network or it may be road network or railway network. Yeah, now this is activity for you. Please write 0, 1 on your books, pages, whatever. 0, 1. You have written 0, 1. Okay. Now add 0 and 1 and go on, like this you should maintain. How I have maintained, no? Like that you write 0, 1 and then you add 0 and 1. Then you write. Then you add 1 and 1. That you write. Are you writing or you are just looking at me? I am here only. You can take my photos and all afterwards. No, and just in case you, not that you should take, but I am just saying. Or you want my autograph or something, that I will give you later. But now you do adding. But that is my wish, that you should take my photo and that you should take my autograph. Not that you should do, it is my manokamana, like that I am telling. Best I am telling, not that you should do. So 0, 1, 0 plus 1? 0 plus 1? They are not sure, I think. 1 plus 1? 2. See, if the nursery students will hear, no, they will feel, kya padha rahi hai, 1 plus 1 plus 1, 2. 2 plus 1, 3. Continue doing that. Continue. You, at least you, oh, madam, you don't know 2 plus 3 also, right? 2 plus 3. Yeah, continue. What will you get next? Good. Next. Add. Oh, madam, there. You don't have pen, pencil. Please provide pen, pencils to them. Organizers, please provide pen, pencils to the people who are devoid of pen and pencil. Donation also, it's okay. You can donate. Where have you reached? Pardon? Further. 89. Very good. Any? Very good. How much? What is that? After 89? 144 will be put now. Government may put 144 if too much damal happens, isn't it? So 144. So what do you find? Is this beautiful? You may think, madam, this is just adding numbers. Being from fine arts, he will know what I am talking about, isn't it? Now you may think, madam, numbers and beauty, wait. This is what we call as the Fibonacci sequence or Fibonacci Fibonacci sequence. You got that, all of you? Because if you don't do it, then you will not enjoy what I am going to do. You have to know it. Okay. So Fibonacci sequence, or we call it as the Fibonacci series. Okay. 0, 1. See, it starts with 0. Just see 0, 1. Simple. And you see from where you can go. You are not doubling or no multiplying, no nothing. Just adding. Adding with the previous. Okay. Now next what you have to do is, you see the divisions I have done. You see the number divided by the previous number. Do that and tell me what you are getting. Take a number and divide by the previous number. So 3 divided by 5, 3 divided by 2, 5 divided by 3, 8 divided by 5. Please do and tell me what you are getting. And go on. Yes, what are you getting? Yes? Sir, how much we are getting? You already know. 1.6, approximately 1.6 or somewhere near 1.6. Am I right? You go on dividing number with the previous number, you will go on getting this. Don't you think that there is something magical about this? isn't it? You get a sequence and then when you divide them, you get 1.6. Now what is so magical about it? Why are we talking so much great about it? That we will see today. Okay, this ratio 1:1.6, you got now 1.6, isn't it? 1:1.6, this ratio is called the golden ratio. And this golden ratio is the ratio which all artists, performing arts, fine arts, they worship this ratio. Because if they can get this ratio, whatever they make is 100% beautiful. On the computer we do, we have Word document and then we put, we say this much should be the margin, this much should be the header, footer. All this is ruled by same. Same formula is used everywhere. You give it to the computer fellow, we say you do the formatting, you give us proper border. He may not know, but he is using this ratio. Computers, they are using this ratio for all kinds of editing, they use this. Anything that you want to make extremely beautiful, all the artists will use this. This ratio, if they get, whatever they make, it is going to be beautiful. Let us see how. Now you see this. Today you have homework. Go and measure. So this you cannot get in beauty parlor. This beauty parlor will not give you. This is measurement. Aisa hai vaisa hi. Okay. So you see there is a ratio. What I am trying to say is that it is not, whether it is human face or human body or animal body, whatever we have seen till now, not abruptly made. There is perfect calculation for that. Are you with me? Okay. So we have proportions. You see the distances that they have taken? You getting? So the face is divided into 3 quarters. You can see that? And if that is like that, you will look like her. And if you don't, then cut some amount of your nose. Attach something to your nose. Now the point is, when we look at the face, it looks, but there is mathematics. That's why I said when something looks beautiful, there is maths behind it. Okay, so that's why I thought that all of you would be interested in knowing, madam, flowers and all, okay, how about us, the selfie, us, yeah. At first glance, it seems like the golden ratio is only a number, but it might be a secret to measuring beauty. Many Renaissance, he is familiar with Renaissance sculptors and artists like Da Vinci, Michelangelo, Raphael, they used to achieve balance and harmony in their works. Some people also believe the most attractive faces show the golden ratio in their proportions. So most beautiful faces, do they have this golden ratio? Let us see. Now this is different parts of so there was a research done. What he did, he took the different parts, he measured every part of the face and he tried to have the golden ratio calculated. Are you with me? So he wanted to know which face, if it is very beautiful, how much of that golden ratio is satisfied by that face. Is that face following that rule or not? So now you will feel, mera golden ratio kaun nikalega? You may feel like that. You only sit with tape like this. Your mother may be thinking, crack or what? She's tape here. Madam said tape. You should do it. You must measure your forehead, measure this. And then if you find it is not golden ratio, don't collapse. Okay? Madam, ab ji ke kya fayda mera golden ratio mein? No, don't do that. It is just for you to know. Doesn't mean that you have to go and, madam, abhi mera heroine hone ka sab chance gaya. Tumko teacher hona hai, heroine nahi. Now you see, and what he did, earlier one if I showed you, he took the, golden ratio for each part. Each part he took that golden ratio. You understood, no? For each part he took that golden ratio, and then what he did, he applied that on each of the models and actors, actresses, and I have brought only a few. I have not brought all. Acha hai heroine. No. Acha hai, aisa math se to bahut acha hai. No. Katy Perry, he found that hers was 90.08%. She is almost, following her facial expression, her facial dimensions are following almost, the golden ratio. Okay, now you see. Bella Hadid 94.35. That means her face is even more closer to the golden ratio. Are you all getting what I am trying to say? Okay, these were all the people whom he measured and he found. And he found there are many, but I didn't bring. That way you will go in some other world. So I brought only 2. So then you will feel, madam, how do I become like Bella Hadid or Kitty? No, 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 you be yourself only. Now the next one comes. Who's this? Angelina Jolie, isn't it? Now you see, this is the real one and this is the ideal one. With computer graphics, they have made the ideal Angelina Jolie and this is the real Angelina Jolie. Are you able to see? In the other one, the ideal one, the computer has tried to make it follow golden ratio to the point. See how she looks? And in the real, she is not fully, golden ratio, fully, but she looks more beautiful in this. Am I right? Yeah. So golden ratio is for calculation, it's good. But the point here is, I just tried to show you that that was good, but you see this. So sometimes, nature will play a little off so that it looks more beautiful. What do you feel? This Angelina looks more beautiful, isn't it? Yeah. So you also, so no need of going and cutting your nose and all that. Now this is something that I want you to do. Look at your hands. You have hands? All of you? 2 hands generally we have. You have? Okay. No, I'm just checking. If you kept one at home or something, I don't know. You have this phalanges. These are called phalanges. These are finger. These are the phalanges. Okay. Now take the, how will you measure now? You have to, at home, okay, you can do that. If you measure your phalanges to phalanges, this part also if you measure to each other, you can find whether the ratio is coming to 1:6. And you can also measure this with your full hand, with your palm up to the wrist, your hand, all this if you collect from your top of your head to your middle of your dorsal here for abdomen and from your abdomen to the stomach. All you will find, they all follow golden ratio. Today you have lot of work, lot of measurement. Plastic surgeons, plastic surgeons? They don't work with plastic, they work with golden ratio. So when the heroine or hero or somebody or people like you who want to be hero, heroine later, don't have to do it, I'm just saying. So they will go there and they say, Mera ye naak barabar nahi. You see, they will end up like Angelina Jolie. You see, she was looking better before. After that, she has not done it, but I'm just saying in case she does. Human hand comes very close to creating a Fibonacci sequence. You remember that? 1, 1, 2, 3, 5, 8. You will find that. And that ratio, 1:6, you will find. So at home, you can go and measure and see. And at home, you can go and see. Sometimes I was telling Vishwesh that very beautiful videos are there where you can see. We can do like this, isn't it? With our hand, we can do like this. Yes or no? Yes. Do it, just try whether it is working or not. Sometimes you have to see whether it is working. Yeah? Now this is possible because of the golden ratio. That's the point. So these phalanges, they work because the measurement is like that. So, and chalta nahi because you are whole day on mobile. That's why you do this exercise little bit. It is good. Okay, when you measure the length of the phalanges in order from, you see, from the wrist. Where is wrist? Wrist, where is wrist? Show me. You have wrist? Yes. Show. No, we have to ask, somebody may not have. So wrist, generally this is called wrist. You call this wrist? We put a wrist watch, that. From wrist to the tip of each finger, you measure. Okay, not now, madam, I will measure, don't come with that, you don't measure. You will find that the sequence of the length is pretty close to Fibonacci sequence. Okay, is it possible that this arrangement of phalanges is helpful or adaptive in gripping objects? We are able to hold. I will give that video to your sir. It is not a video, it's kind of an animation. They have used this to make machines. When you see JCB and all, you see how it looks like a human hand, Am I right or not? So they use this. That's why I said we get inspiration from nature. We are not doing anything other than what nature gives. Everything that we do, we have inspiration from nature. So this, this action. So that's the action that machines do. Robots, they do that. From where they learned? From our hand. And from where they got the measurement? Measurement इसलिए बोलते हैं तुम्हारा नसीब तुम्हारे हाथ में है, they say, Now you know why they say that's the reason, isn't it? We are very close to Fibonacci sequence. This is the golden spiral. This is what I was showing you right in the beginning. We have seen golden ratio. Yes, we have seen Fibonacci sequence, Fibonacci series. Now we are coming to golden spiral where all these things come together. That means golden spiral is the place where your golden ratio and your Fibonacci sequence come together and they give us a spiral. Okay, how this spiral is made, what is so special about it? They, in the arts field, they consider it as divine spiral. Am I right? Divine spiral, and they call it as the divine ratio because they follow this for everything they do. Now let's see how it is in what we see. Can we see this spiral? Anybody can tell me where we can see this spiral right now? Your hand. Your hand, if you turn like this, that is your first golden spiral. This spiral that you can see is nothing but your spiral. You don't have to go anywhere. So I have shown you two things in your hand. Nasib, isn't it? What is worth knowing, this sequence appears in flower petals, tree branches, snail shells, hurricanes and many other objects. How can it be that hurricane, leaves, petals, human hands, same formula? Yes, it is the same formula. I mean, the same idea is, so Fibonacci sequence consequence is the golden ratio that says that the ratio between the number and the preceding number. Just now you did number and the preceding number, isn't it? It's called the phi. Phi is a Greek letter, it's called phi. Like how you have alpha, beta, like that it's called phi. Phi is, so the ratio between any two numbers, consequent numbers in a Fibonacci sequence gives you golden ratio. It is 1:1.6. Now see this, now you can understand? Yes. I will tell you about that square, but this is just for you to know. So the rose flower looks beautiful. Why? Because it follows Fibonacci sequence. How's that? You never knew, isn't it? Isn't it? So that's why I said that. I told your teacher also, bring some rose flowers, we'll have some activity for that. So this is how, is it okay? Are you all happy? You are going on well? Because I am enjoying. Are you enjoying? Yes. Yeah, they're very good students. Now you can see how both come together. You had done the sequence, Fibonacci sequence. Next. Now you see Fibonacci sequence and the golden spiral together. Are you getting? Now, you may need a little bit of explanation over here. Let me see. Can you see one? One. Okay. Two squares. One. Now, you can see here this one square and this two squares. Either two. Two squares ka ek square. Are you with me? Here it was one square ka ek square. Here two squares ka ek square. Here, are you getting? Now what is here? Three squares ka ek square. Are you getting? Three. Okay. Now what is happening? 5. Now what is happening? 8. Now what they have done is they are putting an arch like this. Can you see that? Okay. Spiral. It is coming into the half of all the squares that we are making. You can continue this. You can go on 8, then the next, whatever you made, 144, all that you can do. And you can make a spiral like this. So this spiral which I showed you on the hand and which you had seen on the first slide, they follow the same principle. This is called the golden spiral because it fits into the golden ratio. Because the golden ratio you get from the Fibonacci sequence. Three things are related to each other. The golden spiral, the side of each large square represents the number in the Fibonacci sequence, isn't it? We saw just now 1, 2, 3, 5, 8. They are all numbers from the Fibonacci sequence. While quarter circle arc connects opposite corners within each square. So this square, if it's complete, so you will see. You can see here. You can see they are connecting the opposite sides. See here. You can see opposite angles are being connected by the arc. So it is such a perfect spiral that you can see it almost everywhere. You will be amazed where it can be seen. Just for you to understand, I have brought another picture which is little more simpler. Here you can see it even better, isn't it? Am I right? I brought yet another just to, because I felt that picture may not be. Here you can see the spiral cutting from one corner to other corner very clearly. Can you see that? You see the spiral, it is going from one corner of the square to the other square very clearly. Okay, so it's a perfect spiral. Okay, so you see that? Because it is not just a spiral, it is following a rule, isn't it? It is going according to the Fibonacci sequence, it is Fibonacci ratio, the golden ratio and the spiral. Okay. Now you see, this is something very interesting. This is called phi in nature. Phi is the alphabet that I told you, okay, which represents the golden ratio. Many ordinary flowers use phi. For example, if we were to measure the diameter of the inner petals, we would get 8.5 mm, length of the petals 13.5 mm. If you put the petals, if you divide them, what you are getting? 1.59 is to 1, almost 1.6. That means this flower is also following golden ratio. Are you getting? Isn't it? So number of, now you see the cones. If you this is a pine cone. Each fruit holds a secret. Can we have that? Okay. Maybe somewhere. Here. Can you put it here? Yeah. Yes. Here I have a pine cone. Each fruit holds a seed. If we were to count the number of spirals pointing to the left, we would get 8. If we were to count the spirals pointing to the right, we would get 13. I want 1 or 2 students to come and count. Let's see whether it is true or not. We have to see, isn't it, whether actually pine cone is having or not. Please come. Okay, you see, you have to take a sequence, yeah. Take the sequence and show me if you can get 8 in one direction and 13 in the other direction.
1, 2, 3, 4.
It should go, yeah, correct.
8, 9, 10,
12,
11.
13. One side it will be 13, another side it may be 8. Okay, so you see the arrangement. Why I am saying pine cone, simply it doesn't grow. Other side, are you getting? One side you on the opposite side. Let's see. Means go in the opposite direction.
3, 4, 5, 6, 7, 8, 9.
No, in the sequence you should go. You are going just counting. You diagonally jana hai na. You have to go. Yeah, in a spiral you should go. See how that is shown, no? It's like a spiral. Eight. So it will, because it grows only like that. No, thanks. Please sit. Okay. Now we may wonder why it is having such special, because these are all package. See, when we want to go somewhere, we pack our things, isn't it? We want to take more things in lesser baggage. Am I right or not? So nature also wants to pack more things in less. That nature also wants the same thing. So that is why it finds a sequence, it finds a method in which it can store more things but in less. So that is one way of doing it is two twisted spirals. If it has, then it can manage within little space, it can manage more seeds, because that's what nature wants. It wants to store more seeds. It is not just for beauty, though it looks beautiful. You can also check whether the pineapple is actually having 5 scales, 8 scales and 13 sequence. You can just try and find out before you remove the skin and make juice out of that pineapple. Take some time, check the scales, whether you can say, then your people at home will wonder, what are you counting? Pineapple ke upar counting? So see, maths is there everywhere, isn't it? That is why. You can count on the flowers also. 13. So when you have the petals, when you get flowers, you count whether they are following Fibonacci sequence. You will be able to do that? Yes or no? Number of petals. Now you know what is Fibonacci sequence, isn't it? 1, 2, 3, 5, 8, you know it. So you can easily find out whether the flower that is in your hand, most of the flowers will be having Fibonacci sequence. So you can see that. So don't you think that maths is there in nature? Now you see the amount of spirals. Can you see the spirals? You can see it's coming in your eyes, you see. You feel a little dizzy, no? Yeah. So like that it is there in sunflower. For what? For packing the seeds. It is a packing. It is not to show you the beauty. They are not interested in selfie. They have arranged it so that in less space they want to put more seeds. So this is the perfect pattern to put more seeds. Okay. So as to why sunflowers abide by mathematical rules, scientist theory says it's due to efficiency. Simply speaking, flowers can hold most seeds if each seed is separated by a irrational numbered angle. Now irrational numbers you are learning, isn't it? When sometimes you are studying maths, you may be studying about irrational numbers. So the angle that they are having is irrational number. So you see so much of detailed mathematics is there in the arrangement of seeds of sunflower. Do you think maths is not there in nature? Isn't it? So it is marvelous. The same thing I wanted to show. So I thought that we have actual things also you can see. So the seed pods of pain cone come in a spiral arrangement. They have two spirals. Okay. Each of these twists upwards in opposite direction. Most time the step number will match the pair of consecutive Fibonacci numbers. It may be 5, 8 or 13 or whatever. Now you see tree branches also. We may think that trees just have branches and they just sprout. No. A tree's main branch grows till it produces a branch, creates two growth points, then one of the new stems branches into two, the others remain dormant. This process repeats each of the new stems. This pattern is also appears in the root system. So when we see the roots, when we see the branches, they follow a system. They simply don't branch up and show all kinds of flowers and leaves coming there. So everywhere you will find Fibonacci sequence most of the time. Sometimes they may be violating, but most of the times they have got one or the other sequence that they follow. It is not abrupt. That is what I am trying to say. It haphazardly, no plant, no animal has got a shape or whatever they do. Nothing is haphazard in nature. Now you see, can you see the branching? Can you see the sequence? Yes? Yes or no? Fibonacci sequence is there in the tree branching. See how beautiful it is, isn't it? It looks beautiful, but it is following the sequence. Simply it doesn't grow. Okay? So growth follows a sequence. All the growth, whether it is human growth or this, it follows the sequence. There they cannot see the numbers, I think. But the numbers are there. On the top, first level is 1, 1. Then the next level is 1, 2. And the next level is 3, 2. It is coming like that. It is downward, it is coming. And the main one down, it will be 21. Down the main single trunk, that becomes 21. So you have to go backwards. If you put, you will get. Are you getting? It is not from down 1, no, it is from the top 1 to downwards, it will come up to 21. You know how it comes. Okay? Is that interesting? Yeah? I found it very interesting. This is another example that I wanted to orb web spiders. Spiders we have seen. You have seen spiders? Yeah. So spider, we remove them, isn't it? Correct, no? Diwali, remove. Christmas, remove. We remove spiders. But have we looked at the art with which they make? Can we make the spider web like the way they make? We can only bring one nice broom and clean it. Isn't it? Vacuum clean it so that no spiders are there. But let us see what spiders can do. Isn't it? Orb-web spiders are divided in about 5,000 types of orb-web spiders are there. They all make almost perfect circular webs. Circular. Okay. With near equal distance. If I ask you to draw a circle, you know how to draw a circle? Please draw. Try. I am not coming. Draw a circle and you ask your neighbor whether it is looking like a circle. Yeah. Spider can do. I want to know whether human being can do. I don't know whether. Spider is making circular web. No protractor, no pencil, no paper, no nothing. Okay. It didn't go to 10th standard geometry class. Spider doesn't know. Circle has got 360 degrees and all those things. Spider doesn't know. But spider makes. But we are to Baba very intelligent. So let us see whether you can make one circle. And your neighbor said it is circle? Because they are your friends, they said. Do you think it is circle? It may be, yeah, only one honest person is there in the entire hall, see. Yours may be looking circle to you, yeah. Now you put radius to that, equidistant radius. You know radius? From the center it should start, huh? Kanchan you don't put radius. From the center to the circumference becomes radius. Kanchan bhi dalne ka nahi. So from the center you draw radius. Okay, you have drawn, no? Very good. You have drawn, yes or no? Now you draw equidistant. That means more radius you should draw, but the distance between the radius should be equal. Try. Equidistant. That means all the radius, kanchan bhi aisa nahi. You should draw like how we have the chakra on our flag. On the flag we have the chakra. It has got equidistant. No, like that you draw and see if we can get equidistant. By the time you draw equidistant. Now, why I am saying a spider can do. That's what I am saying. We are struggling and the spider can do. For that I am saying. Okay. So, not that I can do, but I am just trying to show you that how difficult it is for us, but a spider can easily do it. Okay. Equidistant radical supports that comes out of the middle as well as a spiral they weave to catch prey. Let's see. It remains unclear how orb web spiders, they are called orb web spiders, that's the name of the spider, are geometrically inclined. How they know this geometry? We don't know, but they know it. As shown by test, orb webs do not catch prey better than irregularly shaped webs. As per some scientists' theories, we put it there, the next one. Yeah. Orb webs are made for, now you see this is how the web of a orb web spider looks like. See the neat work of that orb web spider. Can you see? Equidistant. See the distance? Not less, not more, all equal. Nice, no? If I ask you to draw like this, don't try. Don't even try. Pizza, if I give you, of course you will not give it to anybody else, that's a different story. But if I give you round pizza, mostly pizzas are round only, and if I ask you to cut and give it to 6 of your friends, first of all you will tell 2 of them to go because you can't divide into 6. So what you will do, 4 is easy, 2 is better because 1 is the best. No need of dividing. Okay. So that is why you are not able to draw the radial in the circle. Reason is that because if pizza is there, you will tell your friend, I am not at home. So no need of dividing. So if you are to divide, it becomes so difficult, no? Why it is difficult? Because you don't want. That is the main. Otherwise you can divide. Okay. But you look at this orb web spider. See the efficiency with which it is doing. So beautiful it is. And there is the one type of orb web spider. What it does, in the center here in the center, it will make, like kind of a mess kind of a thing it will make. You know why it is making? I was just reading about it. It makes so that the birds don't come and get entangled in, because birds are not the prey for the spider. So spider's entire effort of making the spider web goes waste if the bird will come and hit. So to avoid a bird coming and hitting, what it does, in the middle, when you go to the jungles and or when you go to Bondla or somewhere, some forested area, you will find such webs where they call it signature. The spider puts a signature so that the birds don't come and hit, because once they come and hit, the spider has to again put all effort to make it, isn't it? So orb webs are made for strength. Radical symmetry helps evenly distribute the force when a prey makes a contact with the web, which makes fewer rips causing to the. So if one insect comes and if the whole spider web falls, the spider has to make it again. So if he makes it like this, then what happens? More prey can come and stay, and still the web will remain good. So what I am saying is that look at the marvel of nature, that they are using geometry, they are using radial symmetry, everything they are using for their own benefit. Yes, anybody can count the number of petals in the rose flower? One person, just count. Let us see. Count the petals. You don't have to do anything. No sing song, no dance, no nothing. Just count. Let us see if this rose flower is going according to the Fibonacci sequence or not. One more person, you can also come and count this. Maybe you can count another flower. Count this. Let us see if Fibonacci sequence is there or not. Or it is violating. We don't know. Nicely they are counting. See the number of petals in a rose flower? We just give. See the number of petals? It takes time for them to count the petals, isn't it? Have you ever counted petals in the rose? Now you will count. 27. How much? Many more are there, no? But still, how much?
47.
47, isn't it? So here what we are trying to say is, when you are counting, next time when you count, you see whether the sequence, like that. So next time you count the flowers, petals of a flower, and see whether it is following Fibonacci sequence, number of petals. Will you do that? Before you throw the flower, count. Now you see, similarity I want to show you. What is the first one? Anybody can tell? Elephant's trunk, isn't it? Elephant trunk's turn. What does it represent? Pardon? The golden spiral, isn't it? And the next one, anybody? It's a fawn, isn't it? Fawn turned. Third one? What is it? Horn of a ram. Horn of a ram. Okay. This is a shell, isn't it? This one? Galaxy. This one? Pangolin. Now you see, these are all so different, but they are all having the same, isn't it? Isn't that wonderful? Right from galaxy to elephant's trunk, everything. Now you see this. Did you ever think that cyclones, same pattern, and the cephalopods also, the cephalopod just now I showed you. How do you feel? Yeah, isn't it amazing? Same golden spiral, hurricanes, cyclones also, and crustacean cephalopods also. How's that? Chameleon's tail. Chameleon's tail, and what do you find? The egg that you just take and break and eat. Now you should have some respect, because the shape is following golden spiral. You will forget that? No. And how will you crack the egg? Which side you will crack? You will crack it like this or like this? How will you crack? In this position or in the other position? This position, isn't it? In the other position, it will try if it can crack. It will not crack, isn't it? When you take the I'll make omelette, you just take one. You don't have any regard, no respect for that egg, you just break it. Now you should break the egg with respect. These are called broccoli, Romanesque broccoli. What are they? Romanesque broccoli. You know broccoli? This is a special type of broccoli. Can you see the same spiral, the same formula used over there? Nature uses the formula so well, isn't it? And it brings out different beauty. Same formula, but beauty is the same. Now you see, full comparison. What you can see here, some of the things may be repeating. You can see, here it is the shell, here it is universe, and here it is the sunflower. Here it is aloe vera plant. Aloe vera, you know, aloe vera plant. Here, hurricane, isn't it? Cyclone. Here, fern, some kind of a fern. Here, waves. Here, finger thumb. Again, same thing. What did I tell you? No, what did I tell you about your hand? Naseeb. Told you, no? Yeah. Now you see here. Tree branching. You remember that? The veins branching. Lightning. And lungs, arteries. What a formula of a universe. Are we not one? Isn't it? The same formula of a lightning and your heart and your, for example, lungs. What a formula. Same thing for you to just, sunflower, beautiful. Yes. Next. How's that? Elephant trunk is also following the same principle, and the water coming out of the elephant's trunk is also following the same principle. What a nature. Isn't it marvelous? Yes. Next. This is a very, could not do anything without this spiral, golden spiral, all this ratio. And you see how they have used that spiral. Isn't it a beautiful painting? It's a very famous painting. I felt that, and they have tried to, you can see in the second picture, the spiral is put. You can see its overlay is there of the spiral. See, I just thought that snail and human thumb, so much of similarity. So we don't have to be too proud. Snail will say, I am also like you. Correct, no? I think with that I will end. Other than if we can show these two videos, maybe you can show. Otherwise, thank you for being a good audience. Enjoy the maths day, remaining part of the maths day.